So linear operator, let me just again remind you what was the definition. Linear operators. So let's say there's an operator A acting on a vector space. Let's say S. So linear means what? What it means is that if I take two vectors, alpha, say A plus beta B, where A and B belong to S, obviously this also belongs to S. So the action of A acting on alpha A plus beta B. I mean, in general, you see, I should first mention that. I don't know whether I mentioned this already last time. So an operator A will map S to what? To some, in general, some another vector space. Let's say S prime. Okay, another vector space in general. So in particular, you remember that when we discussed the dual vector spaces, we introduced linear functions, right? In fact, the dual vector space was nothing else but the space of linear functions. Function is a special case of an operator, because in that case, what do? Functions map vector space to complex numbers, real or complex numbers, depending on, right? So that's just a special case, right? Because set of complex numbers is also a vector space. Right? It's a one-dimensional vector space, one complex dimensional vector space, right? Or set of real numbers is again a vector space, because you can check that all the properties of the all the definitions of the vector space are satisfied for the set of real numbers, addition, multiplication, all that which is there, right? So that's a special case. So linear function is also an operator, but it is a special operator. It maps the vector space to either real numbers or complex numbers. But now there's a generalization. So we are saying that linear operators are some operators which map a vector space in general to another vector space. Okay, but we will specialize. In fact, most of the discussion, most of the in physics, the most useful situation is when this S prime is S itself. Okay, so this operator maps a vector in S to another vector in the same space S. Okay, so we will specialize. So we will specialize to the case. Where when S prime is in fact equal to S. So it's mapping a vector to itself, to the same space. Okay. So therefore what we are saying is that what it means is that if A belongs to S, then A acting on A also belongs to S. That's what we are doing. Okay. I'm just trying to define what do I mean by linear. Linear means that it satisfies the condition that this acting on A acting on this state, which is an element of S, is the same as alpha A plus beta A B. You see, this A acting on this vector A is again some element of the same vector space. This is also an element of the same vector space, and then you just add them up, right? Because it's a vector space, so there's a notion of adding. So this, of course, belongs to S again. So this is the meaning of linear operator. This will be very important. I mean, in fact, in quantum mechanics, all of this, the physical observables will be linear operators acting on now a particular vector space, which is the Hilbert space of states. So it will be infinite dimensional space. For example, Hamiltonian is just is an operator which acts on the Hilbert space, momentum operator. All of these physical observables will be operators acting on some Hilbert space, and those will be linear operators. So this is a very important. This is a very important concept. Linear operators. Okay, I mean, I will come to examples, but let me. Okay, so for example, let's see as an example. Let me just already give some example. Let me first consider a finite dimensional example. Okay, so let's consider a finite dimensional. I mean, the vector space S I take to be the set of all n cross 1 matrices. So which means column vectors. So these are column vectors. In other words, these are column vectors. So this is an n-dimensional vector space. Set of all n cross 1, either real or complex, depending on, I mean, it's up to you to choose complex matrices. And choose A to be some n cross n matrix. Okay. And then, so the A will act on these vectors by just a matrix multiplication. Okay. So you have an n by n matrix, and this is an n cross 1 column vector. So you can multiply. The result of multiplication will be, again, an n cross 1. Right? So let's see. So what we have is, so take A is an element of S. That means A is an n cross 1 matrix, which means it's a column, right? With say A1, A2, up to AN, right? This is a vector in this example. And A, capital A, is some n cross n matrix. So it will be like this. So let's say A11, A21, etc., right? And so on. I mean, okay, let me just put everything down. A11, A12, A13, and then A21, etc. AN1. So this will be the matrix. And we define the operation. So how this operator A acts on this vector? Simply by matrix multiplication. So when you multiply, like matrix multiplication, this row will multiply that column, right? And give you, so the result will be some matrix B1, B2, I mean some column vector Bn. Okay. So you see this is an example of a linear operator. You can easily check it's a linear because matrix multiplication will be linear. I mean if I take two vectors, say A and A prime, and add them up, A plus A prime, right? You can easily check. I mean, please check that this definition is linear. This this defines a linear operator. Okay. In fact, we will see. I mean, maybe today itself, we will see that actually this is completely general. Meaning, for any finite dimensional vector space, you can always represent a linear operator as a matrix. Okay. As a n by n matrix. So it's completely general. We will see that in a moment. Okay. I mean, not in a moment, but okay. By today, I think we'll see. Yeah.
What about the row vectors?
Yeah, you can do that. I mean, okay. In that case, you have to multiply from the. Yeah, that's also fine. You can define the operation like this. So you have A1, A up to AN, and then multiply from the left, right? That's also possible. Yeah, you can do it. Yeah, I mean normally people use this convention, right? But also you could have used that convention. Another operator. Let's see. So consider now the set example, set of functions. Set of functions on, say, a real line or whatever, functions of one variable. It doesn't matter. It doesn't have to be one variable, but let me just take as an example one variable, say x. So arbitrary function f of x is an element of that. And this forms a vector space. We already saw it forms a vector space, right? Under the rule of, so how you add point-wise. If a function f1 is given and f2 is given, then f1 plus f2 is by definition, just take at a given point, f1 will be some number, f1 acting on at that x will be some number, f2 will be again another number. You just add the two numbers, and that defines to another function, right? So it's, I mean, you can plot it. It's easier to plot. So here is my x, and here is, say, so suppose f1 is this, okay? It's some function, so I can always plot it, and f2 is, say, another function. This is, say, f2. Then f1 plus f2 is simply adding. At each point, you just add this plus that. Or here, let's say, this point, you add this plus that. So the result will be something here, right? This plus this will be something, some point here. And then you just, at each point you do that, and then just join them together. So that will be another function. Okay. So this function will be f1 plus f2. So that's the definition. So it's called point-wise addition. At each point you add them up. At each value of x you add them up. So this forms a vector space. Now consider an operator, for example, d by dx. D by dx is an operator. Think of that. I'm just giving an example. So d by dx acting on this function. So I'm going to assume that these functions f's are continuous functions, continuous and differentiable and all that stuff. No? So d by dx acting on that will be again another continuous function. Okay. So let me assume that these are a set of what they call C infinity functions. What it means is differentiable any number of times. Okay. So it's very, very smooth functions. There is no discontinuity. No discontinuity. So even the first derivative has no discontinuity and so on. So all derivatives are defined. Okay. So I consider C infinity functions for simplicity again. So d by dx will acting on f will again give you a C infinity function, because we are saying it's differentiable to any number of times it's differentiable. So this is an example, and it's a linear operator, because if I apply it on alpha f1 plus beta f2, okay, then it just acts linearly. Correct? So a linear operator. In fact, in quantum mechanics, this operator is nothing else but is a momentum operator up to some factor of I, h bar over I, some constant. This is proportional to momentum operator. Okay, so these are just some examples. Actually, in this chapter, we'll focus on the finite dimensional spaces, vector spaces, not vector spaces of this type. But for the moment, let me keep it general. By the end of this today, I will specialize to finite dimensional spaces. But for the moment, I'm talking generally. Now, given an operator, you can of course define take say two operators, A and B, right? Linear operators. Then you can talk about the additions of these operators, right? So, so there is an algebra. Let's call it algebra of operators, of linear operators. If you take A and B, say two linear operators, then A plus B, you can define A plus B in the following way. A plus B acting on any vector A in the S, this is an S, is equal to simply A acting on vector A plus B acting on vector A. You see, this is again a vector, that's a vector, so you know how to add two vectors. So that's the definition of adding two linear operators. So this obviously defines to you another linear operator. Right? You can easily show that this definition implies that this A plus B is also a linear operator. Right? You can just check that A plus B, you want to prove. So let's say take this action on such a vector. You want to show that this is linear. Right? Well, by this definition is nothing else but A acting on alpha A plus beta B plus B acting on alpha A plus beta B, right? And now use the fact that each of these operators A and B are linear operators, right? They are linear operators. So therefore, this is the same as alpha A plus beta AB plus here, again, B is a linear operator, so it satisfies this equation. This is equal to that. Beta B. Okay. Now put these two things together. Yeah. On the other hand, so the question is whether is it the same as? So we want to prove that. We want to check if this was linear. Then it should satisfy this equation, right? That must be equal to. So let's say this must be equal to A plus B, alpha A plus B acting on A plus beta A plus B acting on B, right? That's the definition of linearity. So we want to check whether this is true or not. So that's a question mark here. But then this is indeed true, because you see, just compare, I mean, what is this A plus B acting on A? It is A acting on A plus B acting on A, right? And multiplied by alpha, so these are two numbers, this one and this one gives you that. And this one is again beta A acting on B plus beta B acting on B, which is these two things, right? So indeed this is true. So I mean, so what it is saying is that under this rule of addition of two operators, the resulting operator is again linear, if the original operators were linear. That is one thing. You can also, so this is one, so this is one operation. So we have a set of linear operators, and in that set of linear operators, I can introduce a concept of addition of two operators. So in the example that I discussed, for example, this finite dimensional case where the matrix A was an n by n matrix, right? And similarly, matrix B will be some other n by n matrix, right? And this addition is simply adding the two matrices, right? So that would be example. You can also define a concept of multiplying by some numbers. So suppose alpha. So alpha A, right? If A is an operator, you can define what you mean by alpha times A, where alpha is some number, real or complex, depending on whether it's real vector space or complex vector space. And this you can define is simply this acting on A, any vector A. I mean, this operator acting on that is simply alpha times A acting on A, right? I mean, after all, this is a vector, right? And you know the definition of multiplying by a number, right? What is the meaning of taking a vector and multiplying by a number, right? That's a definition that's included in the vector space, definition of vector space. Okay, so this is the way you define the multiplying by number. But what is very interesting, which is something which is not seen in the vector space, but on the set of operators, you can actually define a notion of multiplication of two operators. You see, this is a multiplication of an operator with a number, right? But now what I'm saying is that I can also define, I can give a definition of multiplication of two operators, right? So how do you do that? So if I want to define what do I mean by A times B. So there's a definition now, right? So A times B acting on any vector A, this is an arbitrary vector of the vector space S, is by definition, so this is something I'm defining, this is by definition, first you apply B on A, whatever is appears on the right hand side. So first you apply B on A, this will be some vector of S, right? And on that you apply A. Okay? So this is the definition. Okay? This is equal to that. Okay. So you want to prove that this definition again, this is again a linear operator. You want to prove that, that this is also a linear operator. So let's prove that. So we want to check. So A times B acting on, say, a linear combination of two vectors, right? So we want to check whether this is equal to, this is a question mark. I want to check whether this is equal to alpha A times B acting on A plus beta A times B acting on B, right? This is a question mark here. If it is true, then we say then this is a linear operator. So let's apply the definition. So from the left-hand side, let's start from left-hand side. I use the definition of what do I mean by A times B. Well, that's nothing else, but first you apply B, and then you apply A. So B applied on alpha A plus beta B, right? That is the definition of the product. But now you use the fact that this is a linear operator. So therefore, this is equal to, okay, A is still acting on this whole thing. But here I use the linearity of B. So that is the same as alpha B A plus beta B. So here I've used the linearity of B. And now you use the linearity of A. After all, this is this sum vector, this linear combination of two vectors. So then I apply linearity of A. So that's alpha A B A plus beta A B B. Right? But this is the same as that, because this by definition is first you apply B on A, and then on that, on the result, you apply A. That's this. And similarly, this is that. So you see that this product rule, the product rule that we have defined here, right? It's a linear. It gives you a linear operator. So that's the new thing. You see, so what I'm saying is that the set of linear operators is a vector space, because it satisfies all the, I mean, the definition I gave, A plus B. Under this addition, it's a vector space, right? But there is more structure than that. It's not just the addition. You can actually define multiplication of two elements. Okay? So there is more structure to this than just the vector space. Okay. However, I should caution you that A times B in general is not the same as B times A, right? Because if I take B times A acting on a vector A, this should be, first you apply A on the vector A, then on the resulting vector you apply B. These two need not be equal, right? In general, they may not be equal. In fact, in the case of the finite dimensional example, where I said each of these operators are matrices, n by n matrices, right? So you first apply the matrix n by n matrix on this n column vector, then you apply the matrix A. So that's the same as a matrix multiplication, right? And you know, in matrix multiplication, A times B is not the same as B times A in general, right? Okay, some special cases it may happen, but in general it will not be equal, right? So this is a non-commutative algebra. In general, it is not in general it won't be commuting. The A times B is not in general equal to B times A. So A times B in general is not equal to B times A. In general. In special cases it may happen, but in general it will not be. Okay, so this is that. Now, the fact that we have defined the products, you can also define all sorts of things. For example, an exponential of an operator, right? You can define an exponential of an operator. It's simply, you just, so what is the exponential of an operator A? That by definition is 1 plus A square in this sense, A times A, the way we have defined the product, right? A times A divided by 2 factorial 2 plus A times A factorial 3 and so on. This infinite sum, that will be the exponential of A. Since we have defined the product, the rule of product, you just apply that, but for the same element, A, not A times B, but A times A, and A times A times A and so on. So all the many, you can define functions of the operators, right? I mean, the exponential of A, cosine of A, sine of A, you know. You just make a power series expansion for whatever the function is. And so this is one thing. These are useful again in quantum mechanics, because in quantum mechanics what happens is that Hamiltonian is the energy operator, right? The operator which corresponds to energy. And the Schrodinger equation says that Hamiltonian acting on the wave function is basically up to some factor of I. It is d by dt of the acting on the wave function. So Hamiltonian gives you a time evolution, an infinitesimal time evolution, right? Exponential of Hamiltonian will give you a finite time evolution. If you take exponential of Hamiltonian times a time difference between initial time and the final time, it will give you the time evolution, a finite time evolution. So exponential is again important. I mean, exponential particularly is very important in quantum mechanics. Okay. Now given these operators, you should, the first question you can ask is, well, one of the natural questions you can ask is there an inverse? If I give you an operator, is there an inverse? Inverse in the sense that since I've defined the product, you see. So first question that you can ask is inverse. Inverse in the sense that if inverse of an operator A, you can define actually two different inverses. One is what we call left inverse, which is such that some operator, some linear operator, such that when you multiply this from the left to A, that is identity operator. I will always use, I will, following these notes, I will use E for identity operator. Okay? This is the identity operator. What is the identity operator? It just means E acting on arbitrary A is equal to A itself. I mean, it doesn't do anything. It just gives you back the same vector. That is the identity operator. This is a definition. This is a definition of identity operator. Natural definition of identity operator. But this should be true for all A, for all. Not just for any one vector, but for all vectors belonging to S. If this is true, then you call that operator identity operator. Okay? It is clear E times what it satisfies. E times any operator is the same operator. Right? See, with this definition, you can immediately see A times E is the same as E times A is the same as A. Right? It follows from there, from this definition. So E is the identity as far as the multiplication is concerned, multiplication operators. So now what we are saying is that is there an inverse of A, right? Okay, so this is the definition of left inverse, what we call left inverse. It may not exist always, okay? I mean, there are operators for which there is no left, sometimes there is no left inverse or no right inverse, no? But if there is another operator which satisfies the condition that this multiplied by A is equal to identity, then you say that operator A has a left inverse, and you just denote that operator by this. This is a notation. Okay? What we are saying is there exists some linear operator such that when you multiply that operator from the left with A, then it gives you identity operator. If that exists, then you call this operator as a left inverse of A. As I said, it may not exist. For some operators, it may not exist. For some other operators, it may exist. Okay. Yeah.
Yeah. For instance, for operator A, we have left inverse A raised to minus 1 right, and A raised to minus 1 is also an operator. And
Yeah.
for it, can I say it has a right inverse, which is A?
Yeah. In that case, this would be the right inverse of that operator. Yeah.
So
Correct.
what makes it different? Just say left and right.
No, but this will be a right inverse of another operator, right? Now I'm talking about right inverse of the same operator A. Yeah, correct. Yeah, but I mean this will be a right inverse of that. Huh? So similarly, you can talk about the right inverse, and it's by definition an operator which you multiply from the right gives you identity. So if there exists an operator such that when you multiply from on the right to A, then it gives you identity. In that case, you say this has a right inverse, and you denote it by AR inverse. Huh? This is just a notation part. Huh? I'm saying there exists an operator. If there exists an operator like that, then you call this. Huh? Okay? Yeah.
So can an operator have both the right and the left side?
Sure, it can happen. Yeah. So now I'm going to just prove some theorem. I mean, I'm going to state some theorems. Huh? So one of the important theorem is that if there is an operator which has both left inverse and right inverse, okay, then they are equal. That's and it is unique. Okay. So let me just try to. But first of all, is the definition clear to everyone? Right. So one theorem is that if AL inverse and AR inverse both exist for some operator, both exist for some A, then AL inverse is equal to AR inverse and they are unique. So uniqueness issue is also important because, I mean, suppose there is a left inverse, there is no guarantee that there is not another operator which also satisfies the same equation, right? It could have happened, right? So it's not necessarily it's unique. But what this theorem is saying that if both exist, we don't know whether they are unique at the moment. All it's saying is that if both exist, then they are the same and they are unique. Okay, that's what this is saying. So let's try to prove that. Well, I mean, so in this case, we have what we are saying is that AL inverse times A is identity, and A times AR inverse is identity. So let's do the following. Let's multiply this equation by A right inverse from the right. Okay. So multiply here AR inverse, multiply this from the right. So what will I find? AL inverse, A right inverse is equal to identity times A right inverse. But we already saw that identity multiplying any operator is the same operator, right? So this is the same as A right inverse. Okay. Now take this equation and multiply A left inverse from the left. Okay. So multiply now this equation by multiply by AL left inverse from the left. So multiply both sides of this equation by A left inverse from the left. So from here, left hand side simply is A left inverse, A times A right inverse. Okay. And on the right hand side, you get A left inverse times identity, which is same as A left inverse. Okay. Now compare these two equations. You see the left hand side of these equations are the same, right? A left inverse, A right inverse. This is also A left inverse, A right inverse. So left hand sides are equal, so therefore right hand side must be also equal. So that proves this, A left inverse equal to A right inverse, right? And the uniqueness immediately follows, because suppose there was another let's call it A left prime inverse, something else, another guy. Okay, but again you go through the same argument, then you see that you will again find that A left prime inverse is also equal to A right inverse, right? So for uniqueness, you go through the same thing prove by basically a contradiction. Suppose there was another A left, let's call it A left, give some name to that, A left prime inverse. So there is another guy, another left inverse of the same operator A, okay, which means of course again A left prime inverse times A is also equal to identity, we are saying. Then go through the same analysis, but now same steps, but just replace this by A left prime inverse. Then at the end of the day, you will prove that A left prime inverse is equal to A right inverse. But A left inverse was also equal to A right inverse. So therefore, A left prime inverse is equal to A left inverse. So it's unique. That's what it's saying. Okay, they're unique. So the uniqueness is just follows from that. Right. You can actually prove also. There is another part, that another theorem, or okay, I think in the book in the notes, these two theorems are combined together into one theorem. But let me just prove another one. Suppose, say A left inverse exists. So if A left inverse exists and is unique, then A right inverse also exists and is unique. Well, uniqueness just follows from this, and is unique, which that follows from this theorem. Once you, if you can prove that this implies that if this implies that A right inverse exists, then the uniqueness follows from the previous theorem. So you don't need to prove that. So mainly just, that's quite strong, right? It's saying that, because you see, these theorems are valid for infinite dimensional spaces. I've not assumed anything about finite dimensional nature. So, for example, differential operators and so on, these theorems that I'm proving, they're applicable. Okay. So let's do the, so what it is saying is that A left inverse times A is identity, right? That is what. So now let me multiply by A from the left, okay? Then you find, so A times A left, this implies A times A left inverse times A is equal to A, right? That's the, because when you multiply A times identity is again A, okay? That's that. Now, let's do the following. Let's add these two equations. Okay. So what we'll find here, so just add these two equations. Add the two equations. Then what you find, the A times A left inverse times A plus A left inverse times A is equal to A plus identity. Right? I just add. So I just add the left hand side of this equation. So is this plus that, right? And similarly, add the right hand side of this equation. This is A plus E. Now, let's take this operator A on the left hand side. Okay. So what you find, this implies A left inverse, A plus A left inverse, A minus A is equal to identity. Yeah. Okay. So what? Let's try to rewrite it in a way. You see, in all these three terms, there is a factor of A, which is on the left hand side, right? So I can express the left hand side of this equation as the following. This is the same as A times A left inverse plus A left inverse minus the identity times A. You see, left hand side is that. If you open the bracket, you see just the first term is that A times A left inverse times A. That's the first term. Second term is A left inverse times A, which is the second term there. And the third term is minus E times minus identity times A, which is just minus A. So we are saying that this is equal to E, right? So what does it mean? This operator is A left inverse, right? Because when you multiply this operator from the left with A, then you get identity. So this is by definition inverse, left inverse. But we are saying the left inverse is unique, right? Therefore, this must be equal to A left inverse itself, right? So this is where I've used uniqueness, the fact that it is unique. So what we are saying, this equation implies that this combination is a right inverse, is a left inverse, right? But since we are saying that this is unique, therefore this uniqueness then implies that this is equal to A left inverse. So A times A left inverse plus A left inverse minus identity is equal to A left inverse, right? That's where I use uniqueness. Okay. And now it's immediate because these two terms cancel. A left inverse cancels. And what it is saying is that A times A left inverse is equal to identity, right? So this implies that A times A left inverse is identity. And therefore, this is a right inverse also, you see. So this implies A left inverse is in fact a right inverse. So right inverse exists and the two are equal. Okay. You mean going from here to here? So okay. So you agree up to this point. This equation you agree. Now what we are saying is this particular operator. Let me just give it a name. Let's call this operator B. So B times A is identity. So B must be left inverse of A, right? So that's why I said. So this B is a left inverse of A, right? Is a left inverse. But now I use a uniqueness, right? The statement of the theorem includes this thing. This was one of the conditions of the theorem, right? That A left inverse exists and is unique, then it's only then that we are proving, right? So I have to use this fact also. Right? Uniqueness then therefore says that this operator B must be equal to A left inverse itself, right? So that's what I use. So this operator B is equal to A left inverse. And then going from here to here, you basically just cancel these two parts because they are identical, right? And then take the identity on the other side, so you get A times A left inverse is equal to identity. So what is it? I mean, what it is saying, there is some operator here, which when you multiply from the right to A, you are getting identity. But that was the definition of A right inverse, right? Right? If there is what we are saying, if there is some operator, let's say C, such that A times C is equal to identity, then this is the right inverse of A, right? So, but here we are saying this A times A left inverse is identity. So this guy is the right inverse of A, right? Yeah, that's what. Yeah.
Can we say the same about the right inverse?
About the
right inverse?
Yeah, surely. I mean, exactly in the same way you can prove. So if A right inverse exists and is unique, then A left inverse also exists. You can prove it. I mean, exactly the same steps. You can prove that again. Okay. Right. I mean, for the matrices, this is the thing you know, right? I mean, in the finite dimensional example I gave, where A was an n by n matrix, right? If the inverse of the matrix exists, I mean, then the left inverse is the same as the right inverse. This, I think you probably have seen it, right, in your undergraduate studies. Okay, if you have not seen, I will try to go through that when I discuss the finite dimensional case. But let me just give you some example of this. Let's see. I mean, just again, you see that if I take this d by dx operator, you remember that was one of the example I gave, d by dx operator acting on the set of functions. Now this acting on, what I'm saying is that this has no left inverse. This operator has no left inverse. Okay, so this has no left inverse. But it has a right inverse. But it has a right inverse. However, of course, the fact, I mean, from this theorem, it's also clear that, I mean, if the right inverse exists and if it had been unique, then there should have been a left inverse. But the fact, what I will show to you that there is no left inverse, that also implies that this right inverse is not unique, right? Okay. So to take the example, let's say, so d by dx is acting on set of all functions. So take a particular case, constant function. The function is just constant. Okay. There d by dx acting on that will be 0, right? So any operator acting on the 0 will again give you 0, right? So there is no left inverse, because if the left inverse existed, left inverse, if the left inverse of this operator existed, then that multiplied by this should have been identity. But identity acting on a constant function should give you again a constant function, not 0, right? So that implies that left inverse doesn't exist of this operator. So let me see. So suppose there was a left inverse. I will just call it d by dx inverse. This is a notation. So then left inverse. So this times d by dx should have been identity, right, by definition. But now let's apply both sides of this equation on a constant function, right? I mean, the vector space was arbitrary, the set of all functions, right? Smooth functions, let's say, set of all continuous differentiable functions. In particular, a constant function is also a function, right? Constant function, by that I mean, take, this is my x-axis. Constant function is simply this. At each point, it is the same value. This is a constant function. So take the special case where f of x is some constant c. Okay, this is some constant, independent of x. That's what I mean by constant function. So apply this on the c, on this function. Right? D by dx acting on c is 0. Right? So this is the left hand side is 0. I mean, this part is 0. right? Whereas the right hand side is identity operator. Identity operator acting on C will give you C. So there's a contradiction, right? I mean, this side gives you 0 acting on that, but this side gives you C. So there's a contradiction. So this doesn't exist. This does not exist. Okay. On the other hand, the right inverse exists because I can explicitly construct. So let's consider an operator B, let's say, which acting on f of x. What it does, it gives you integral f of x, f of y from dy, where y goes from some fixed value, some fixed point x naught, let's say 0, to x. Okay. This is a linear operator again. You can immediately see this is an integral operator. It's again a linear operator. So this is the way the B acts. This is a definition. I'm saying that this operator B acts on a function f by integrating that function from 0 to x. I mean, this is going to be some function of x again, right? This result. So it's a mapping a function to another function, and it's a linear map. And now let's apply a times, I mean, this d by dx times b acting on some function f. Right? Well, b acting on that by definition is this. So this is the same as d by dx. I mean, d by dx acting on the result of b applied on f. But b applied on f is by definition that. Yes? And now apply d by dx. The x appears only in the limit point, right? So d by dx acting on that is simply going to be f of x. This is going to be f of x. Right? Is that clear? So you see this is identity operator, because this operator acting on f is giving you back f for arbitrary f. Right? So this is identity operator. Therefore, b is the right inverse of d by dx. Right? I mean, this was by definition right inverse. So you see right inverse exists, but not left inverse. Okay? So therefore, it must imply that this right inverse is not unique. Right? And indeed, you can see, you can add to, you can define now a b tilde, which is simply acting on f gives you this 0 of x f of y dy plus an arbitrary constant. Right? This will also satisfy the same. This will also satisfy d by dx times b tilde is identity, because all that will happen. So if you apply now, if you consider this d by dx times b tilde acting on any function of f of x, it will again give you back function of f of x, because this is the same as d by dx times b tilde acting on b tilde acting on f, but b tilde acting on f is that plus a constant, right? Now d by dx acting on that just simply gives you f of x, right? But d by dx acting on the constant is 0, so this result is again f of x. So this is again another right inverse, and b tilde is not the same as b. You see, they are different. So there's not a unique. Actually, there are infinite number of inverses, because the C is arbitrary. Infinite number of right inverses. So here's an example where you see right inverse exists, but is not unique, okay, and left inverse doesn't exist. But for the finite dimension, this is of course infinite dimension. This happens because it's infinite dimensional case. In infinite dimensional, there are subtle things that happen, and this is an example of that. Then subtle things happen. Finite dimensional cases always, if left inverse exists, right inverse also exists, and both are unique. Finite dimensional cases, we will see. I mean, so any question on that, on this? I mean, basically the reason why this is happening, and this is a very general situation, and that is because the operator that I started with has what we call zero mode. Zero mode meaning this annihilates some states, some non-zero states. That's what is happening, right? Because d by dx acting on this, which is an element of the vector space, non-null, it's not a null element of the vector space, right? It annihilates it, right? So when such thing happen, you say that this operator has a 0 mode, meaning it has a 0 eigenvalue. Okay? So when such things happen, then there are the subtle issues come. Okay? Subtle things can happen. Okay? All right. So so now let's continue. I mean, so far in this entire definition, I have not used any other structure of vector space, right? For example, whether the vector space has a scalar product defined or not. Huh? But now let us consider a situation where vector space also comes with a scalar product. Okay? In that case, you have more structure, right? So you can also give more structure to the set of linear operators. Okay? So let's consider now the scalar product is defined. So suppose the vector space S, where all these operators are acting. So let me erase this. This is done. Okay. Suppose S. Suppose a scalar product is defined. Defined on S. But what it means is that we have a definition for any two vectors A and B belonging to S. We have a definition B. This satisfies all the definitions of the scalar product. We have a concept. This is some real or complex number. So yeah, depending on whether it's real vector space or complex vector space, which satisfies those conditions that I had defined earlier. Right? Scalar product satisfies some conditions. Okay. So given this, then you can define a concept of an adjoint of an operator. Adjoint of an operator. So then we can define adjoint of an operator, of a linear operator, say A. Okay? And it's defined by the following equation, that you take say B A dagger. I will always denote this is a notation. You see, adjoint of an operator A will be denoted by A dagger. This is the notation. But now I'm defining what do I mean by that. This is nothing else but A B complex conjugate. Okay. So what I have done here, so I have exchanged the order. You see, this was A dagger acting on A, and then you take the scalar product with B, right? Here, A is acting on B, okay, and then you take the scalar product of A. This will be some complex number, right? You take the complex conjugate of that. So that's the definition. Okay. So this is a definition actually. The definition of that adjoint operator. Okay. You can. This is again a linear operator. You can prove that. So now, this is for all. This should be for all A and B belonging to S. Okay. So for all A and B belonging to S, this is the definition. So the adjoint of an operator is that operator which satisfies this equation for all A and B. That's there. Okay. So you can now, I think I will not try to prove this, but you can prove the following statements, that A times B dagger is the same as B dagger, A dagger. Okay? Try to prove this statement, just using this definition and the definition of the product. Try to prove that. Prove this. Okay. Is there anything else I have to say about here? Okay, I think when I discuss finite dimensional case, I will explicitly construct to you what is a dagger. Huh? I will explicitly work out, given an operator A, what is its adjoint. I will explicitly work out that. Huh? But for the moment, this is just a definition. When I go to the finite dimensional case, I will construct it. In the infinite dimensional case also, we will construct it, the adjoint operators, but we will do that in the last chapter, 4th chapter. So towards the end of this course, we will do that. Because that is the way you construct the Green's functions, actually. So you have to define, I mean, in the whole steps to construct the Green's function, you need to define the adjoint operators and so on. For the differential operators, the adjoint of differential operator. So we'll do that when we discuss differential equations. That will be the last chapter. So now I'll be, today I will I'll work out finite dimensional case and construct explicitly what is a dagger. But for the moment, okay, just do this. Then further definition. Okay, if a dagger happens to be equal to a, this is not always the case, but if that happens, then you say that a is a Hermitian operator. Hermitian operator. That's a definition. So if it happens that a dagger is also equal to a itself, then you say it's a Hermitian operator. Okay. In quantum mechanics, all the physical observables will be Hermitian operators. Okay, that's an important point. I mean, that's a very important kind of rule in quantum mechanics. That for every physical observable, like energy, momentum, angular momentum, all these physical observables, right? The operators which correspond, which appear in the quantum mechanics, they will be Hermitian operators. Like the Hamiltonian, momentum operator, angular momentum operator, they will all be Hermitian operators. That's crucial. Because as we will see, one of the reasons is that all the eigenvalues of Hermitian operators will be real. Okay? And of course, the energy is real. Then what you measure is real, right? Momentum is real. So, and that's Hermitian operators have this important property, which we will see in a little while. Okay. What else I can say? Then there are various definitions. Let me just define. So there are another definition. By the way, just usually then for the notational purpose, usually an Hermitian operator will denote Hermitian operator by H rather than A. A is a generic operator, an arbitrary operator, linear operator. But when an operator is Hermitian, we will use the letter H, so that H stands for Hermitian, right? So you see that when I use notation H, I mean it's a Hermitian operator. Okay, so that's it. Then there's a definition of unitary operator. This again plays a very important role in quantum mechanics. Unitary operator is the one which satisfies the condition, and I will denote it by U. Right? A unitary operator I will denote by U, right? So that visibly you see that, okay, when I say U, it means a unitary operator. But what is the definition of that? The definition is that U dagger is equal to U inverse. Okay, I mean, yeah. In other words, U satisfies the equation U dagger U equal to U dagger equal to identity operator. So U dagger is both left inverse and right inverse of the U. So that's a definition. Okay. Once again, this is important because in quantum mechanics, where it appears is in the time evolution. You see, time evolution. Under the time evolution, this operator of time evolution actually, before I do this, let's look at this here. Suppose, so let me just prove one statement here. Suppose I have a Hermitian operator. Suppose H is a Hermitian operator. Okay. Then, what about exponential? So let's consider now exponential of IH. Okay.
Yeah, we use the
Sorry?
We use Taylor series.
What?
We use Taylor series to write.
Yeah. Correct. Exactly. So that's the way you define exponential. Exponential will be simply 1 plus IH. I is the imaginary number, plus IH square divided by factorial 2, etc. Divided by 2, etc. This series, yeah. So this exponential IH. Then let's consider the adjoint of this operator. First look at the adjoint of this operator. Okay. So what I claim is the exponential of minus IH is the adjoint operator, is adjoint to that. Is adjoint of the exponential of IH. Okay. The reason is very clear because when you take the adjoint, there's a complex conjugation, right? So let's maybe go step by step. There are several steps here, so let's do that. Okay. So we have H is Hermitian, so H dagger is same as H, right? What is the adjoint of IH? That will be minus IH, because in taking adjoint you have the complex conjugation. You remember the definition of the adjoint, where on the right hand side appears a complex conjugation. So when you multiply by I and take the complex conjugate, it becomes minus I. So that's the, I mean, just check it with the definition. It's immediate. Check it using definition of adjoint. So now you can see that after all, IH, exponential of IH was that, right? So what is the adjoint of that? You take term by term the adjoints, right? Adjoint of this will be minus IH. Adjoint of that will be minus IH whole square, etc., etc. So therefore, that resums into exponential of minus IH. Okay? So this is one. This is an important property. Adjoint of that is this. And now you see that take the product of these two. In the exponential, they add up, right? The exponents add up. So these two, this becomes exponential of minus IH times exponential of IH is simply exponential of 0, which is 1, right? Identity operator. So this is indeed the inverse of, so adjoint is the inverse of that operator. So this is a unitary operator. In fact, you could multiply by any real number. Let's say t is a real number. Okay, then this will be t here, adjoint of that. So here the t is a real number. Okay, where t is a real number. Okay. So this is in fact the time evolution operator in quantum mechanics. If you evolve the state by an amount time equal to t, say from 0 to t, if you evolve, then this is the evolution operator. Okay? Time evolution operator. And you see that this is unitary operator, because we see that its adjoint is simply the inverse of that. Unitary operator. Unitary operator is very important, because what it does is you see, so let's say I apply, so I take some state A in S, and I apply a unitary operator on A. Okay, so let's take A and B, two states, arbitrary states in S. Then you apply U on this and that as well. Okay, they of course belong to S. So I'm applying the same operator on both states. Then you can prove that BA is the same as, let me give some name to this. Say this is A prime. Okay, this will be some state A prime. Okay, in S, and similarly this will be this is some state B prime. Right, they all belong to S. Okay. Then what we can prove is that B prime A prime is the same as BA. Okay, this is the important point of the unitary operator. So let's see how to prove that. So first of all, let's apply. A prime is simply UA, and see the B prime is, I mean, this B prime is a dual of that B prime, right? When you take the dual, that becomes, so what is B prime? So let's see. B prime is nothing else but B U dagger. Yeah. How will you prove that? Let's see how you prove this. So let's just to see the proof of that statement. Okay. Because let's see, if I take B prime with any C, any state C, okay, this satisfies the condition. This has a, remember the scalar product satisfies this condition that it's the same as C B prime complex conjugate. Correct? This satisfies that. That's one of the definitions of the scalar product. This satisfies that. But B prime is UB, right? That was the definition. This B prime, the ket vector is that. Is this, and I would take the complex conjugate of that. But this by definition was B U dagger. I mean, remember that adjoint was defined like that. C, right? Now, you see, this is true for every C, that this implies that B prime is in fact B U dagger. So this is the way you prove that. Okay. So now let's, so this is equal to that, and then let's, this will be equal to B U dagger UA, right? I just replace B prime by that. And if U is unitary, this is identity, right? So this is the same as that. If U is unitary. Right? So this is a very important property of unitary operators, that when you apply on the states, the inner products remains invariant. Right? In particular, the norm, the length of the state remains invariant, right? The length of A is the same as length of UA. Okay. This is a very important property of unitary operators. Okay, what else I have to say here? So this has some special operators: adjoint operator, unitary operator, and let's see. Projection operators, that's another concept. Okay. A projection operator. Okay. So suppose, I mean, just to give an example, suppose I consider, let's see, so okay, so let's consider a particular vector space with the orthogonal basis. I mean, remember we proved that it's always possible to choose an orthogonal basis. There was an orthogonalization procedure. Step by step, there was a recursive kind of step, right? If you remember, in the very beginning, not very beginning, last week, I think, week before, I think we did this. So suppose I choose an orthonormal basis. So choose an orthonormal basis. Orthonormal basis, and let me just label them as E1, E2, etc., E3, etc. So this is orthonormal basis. It means EI with EJ is delta IJ. That's okay. So now consider this operator, and let me just call it say P1. This I define as this operator. E1, E1. Okay. This is an operator, right? Why? Because when this acts on some state, okay, what is it going to give me? So I mean, why is it an operator? Let's apply P1 on any vector A. Okay. Well, that by definition, this is a definition. That by definition is simply E1, A. Okay. Well, this is a number. E1, this is a scalar product of E1 with A. That's a number, right? So it's a number times E1, which of course belongs to S, right? The vector space. So you see that P1 acting on any vector will give you again some other vector. And it's linear, you can see that it's linear in A here. A appears only linearly on both sides, right? So it's a linear operator and so on. You can also show that this is Hermitian. P1 dagger is equal to P1. Okay. You can please check this. just using you have to use the orthonormality property of that. So this is an operator. But what is a very special property of this is that square of P1 is P1 itself. That's a very special property of this. So P1 square, let's compute P1 square. Well, P1 square by definition is E1 times E1 E1. I mean, so this times E1 E1. Right? Which is the same as E1 is a number E1. Okay. But this is orthonormal, so this is just 1. Right? So you get back E1. I mean, this is just a 1. So which is P1 itself. So this is a very important property that this operator satisfies. The square of it is itself. Okay. So actually, see, this is such operator. So an operator which is Hermitian and satisfies the property that its square is itself is called a projection operator. Okay. So why is it a projection operator? You see, I mean, in what sense we are saying projection operator? You see, what it is doing, you take any state, right? Whatever, no matter what state you choose here, on the right hand side, it will be some number times E1, right? So the vector on the right hand side is living in a one-dimensional subspace, because it will be always some number times E1. Okay? So that's a one-dimensional subspace. Right? So choose any vector, it is projecting you down to the one-dimensional space. This is exactly like what we do usually. So in the two-dimensional example, if you take some vector thing, and then if you project onto the, say, x-axis, right, then what this projection operator is doing, call this as E1. This direction as E1 and that direction is E2, where E1 and E2 are normalized to 1, length to 1. And E1 dot E2 is 0 because perpendicular. Okay. Then this operation E1 times E1 dot, so this operation is what? P1 acting on some vector V is simply E1 times E1 dot V. Right? But that's exactly, see, this is, say, vector V dot E1. I mean, this vector is nothing else but V dot E1 times the unit vector E1, right? Because after all, if this angle is theta, then this length is simply length of V cosine theta. But when you take dot product of V with this direction, that exactly gives you the length of V times cosine theta, right? So this is exactly the projection operator. It's just projecting this vector to the, say, in the first direction, right? Similarly, you could have defined a second P2 where you have E2, you project on the second direction, right? So that's why, that's the origin of this name, projection, because it's really projecting the arbitrary vector into some subspace. In this case, it's one-dimensional subspace, right? Okay. That's the meaning. It's a very useful operator, it's a projection operator, for this reason. Now, but you can also do a bit more than that. I mean, here this operator was projecting onto a one-dimensional subspace, right? One-dimensional subspace because everything on the right-hand side is going to be simply a number times E1, right? No matter what vector you choose here. For some cases you may want to project into not one-dimensional subspace, but a two-dimensional. For example, imagine you're looking at a three-dimensional space, right? So there is this x, I mean the first axis, second axis, and the third axis. And you have some vector, arbitrary vector, you may want to look at its projection on the blackboard, right? For some physical question, you might want to find the projection. So in that case, what kind of projection operator you will write, right? In that case, you would write simply this. So let's say another projection operator, which is E1, E1 plus E2, E2. Right? This will project onto the first two directions. Right? You can show that this is also a projection operator. Let's take P square. Well, that's the square of that. So, I mean, so that will be simply square of this whole thing here. Okay. Now, so it will be square of this plus square of that plus the cross terms, right? But the cross terms are 0 because this times that is 0 because E1, that will give you E1 scalar product of E1 with E2, but it's orthogonal, right? So this is 0. Similarly, the other cross term is also 0 because that will give me E2 with E1. It's also 0. So only thing you get is square of this plus square of that. But square of this is this itself, and square of this is this itself, right? So you indeed find that this is P. Right? Okay. This is actually quite general. I mean, here to prove this, basically what we proved was that the cross terms vanish. Okay, right? That was a crucial point. I mean, this was a projection operator, that was a projection operator, and the sum is also a projection operator. How that happened? Because the cross terms vanished, right? When you take the square of the combined. You can prove it generally that if P1 and P2 are two projection operators, then P1 plus P2 is also a projection operator if and only if P1 times P2 is equal to P2 times P1 equal to 0. 0 is an operator which maps the entire vectors, every vector to null vector. That's a 0 operator. I mean, I will not prove this. I mean, it's given in the notes. So those of you who are interested, you can look at this proof. But I just illustrated that by this example. Right? Think of this as P1 and that is P2. Then this was null. I mean, this was again a projection operator. Sum was a projection operator. And the crucial point there was that P1 times P2 was 0. P1 times P2 and P2 times P1 were 0. But you can prove, there's a general proof for this. This was a special example. But what I'm saying, there's a general proof. For arbitrary, P1 is a projection operator, P2 is a projection operator. Only that. And then this is also a projection operator if and only if this condition is satisfied. You can look at the proof. I think it's in the page. Yeah, it's in the in the beginning of page 118, 118. Sorry. So these are projection operator. So by definition, P1 square is P1, and P2 square is P2. Right? So the state. I mean, you can see that. I mean, okay. I mean, I will not give you the complete proof, but I just to see. I will prove this way, that if this is true, that is okay. To see that other way, the proof this way, because here it's if and only if, right? If and only if means that you have to prove both ways. Okay. So I will prove to you one way. So let's take P1 plus P2 square. Well, that's by definition P1 square plus P2 square plus P1 times P2 plus P2 times P1. Right? Just open up the bracket. This is P1 plus P2 times P1 plus P2. Just open the bracket, you get that. Huh? Now, P1 square is P1. P2 square is P2 because by assumption these two are projection operators. And then if you assume that also this is true, this is equal to 0, then you see these are 0. So which is the same as P1 plus P2. Okay. But now one would, if you want to prove other way, see here what I did, I said that if this is 0 and that is 0, then this is a projection operator. But you want to also prove other way, that if this is a projection operator, then this must be 0 and that must be 0. Okay? So for that, take a look at this. It's in page number 118. The proof is given page number 118, the very beginning of 118. Take a look at that, and if you have any question, if you have something which were not clear, we can discuss it next time. You ask me and we can discuss it next time. No, because I need to cover a lot of stuff, so I don't want to go through every proof. Okay. I think that's all I want to say about this projection operator. Now let me do some other things. Yeah, still before I go to finite dimensional example, finite dimensional case, let me define one more thing. I mean, what is the point to be proven here is that, of course, if this is a projection operator, then this must be equal to that. That implies the sum of these two terms is 0, right? Sum of these two operators is 0. But it doesn't prove immediately that individually they must be 0, right? So what is done in page 118 is that it also it proves that individually this must be 0. Okay, that is the point. Okay. So other thing is eigenvalues, eigenvalue and eigenvectors. Okay. So if an operator A is given to you, then you consider this equation: A acting on some particular state is equal to some number times the same state. Okay. This is the eigenvalue equation, right? So this is what is called the eigenvalue equation. So if you can find a vector A which satisfies this equation, that operator A acting on this state, on this vector, is proportional to that vector itself. You see, is some number times that vector. Okay, that's what it means. This will not be generally true. It won't be generally true, right? But if you can find a vector which satisfies this condition, then you call A is an eigenvector. I think, yeah, eigenvector of operator A, and lambda is the corresponding eigenvalue. Is the corresponding eigenvalue. Okay. This is a very important point again. I mean, because you already have seen probably in quantum mechanics that finding out the eigenvalues of the, say for example, Hamiltonian is one of the most important steps in quantum mechanics, no? Because that will give you energy spectrum, right? Because suppose this was a Hamiltonian, then you try to look at this equation, then what is the lambda? Lambda is the energy of that particular state, right? So if you can solve this completely, if you can find all the eigenvalues of the Hamiltonian, that will give you all the possible energy levels. You know? So this eigenvalues are very important. This is an important question. It's always very difficult. I mean, if you give me general Hamiltonian, it'll be very difficult to actually solve this equation. You know? But for simple things like harmonic oscillator, etc., there you can completely solve this problem, right? Harmonic oscillator Hamiltonian, that you can solve completely. I think has George done it already? Not. Okay, he will do it now. I mean, at some point. So this is a very important physics problem actually in quantum mechanics particularly. Now it may happen that I mean there is a notion of it may happen that there is no or at least there is some okay, let me take an example. Let me take an example first. Consider this. Let's see. What should I? Consider this operator. It's remember I told you that for in a finite dimensional case, taking n by n matrix, that's a linear operator, right? So in n-dimensional vector space, a linear operator, you can think of linear operator as n by n matrix. So let's take a particular case, two-dimensional vector space. Okay, and then I have an operator A, which is just a 2 by 2 matrix, right? So let's consider this 0, 1, 0, 0. It's a very simple matrix, right? Now try to see if you can find an eigenvalue equation. I mean, try to write down an equation of this type. So we have 0, 1, 0, 0, and x, y. So these are the arbitrary two-dimensional vector is a column vector with arbitrary numbers here, right? And this equation is the same as we are saying, I want to solve this equation. Right? This is the eigenvalue equation for this operator A. Correct? Yes. I mean, this A is arbitrary, right, to begin with. And then you try to find a solution of this equation. So here I started with an arbitrary, and then I want to find a solution of this equation. So this gives you y equal to lambda x, and that's one equation. I mean, you just multiply. Okay, what is this? Left hand side is simply y 0, right? And the right hand side is x and y. So lambda xy. So the first equation is y equal to lambda x, and the second equation is saying 0 equal to lambda y. Okay. Now, if lambda was not equal to 0, then the only solution to this equation is if lambda was not equal to 0, then the second equation would imply y is 0, and then the first equation would imply x is 0. So that is a trivial thing. I mean, you want to find something which is non-zero vector here, right? So if x and y both are 0, then it is nothing. I mean, if you choose this null vector, this is a triviality. So what I mean by here, this equation is that this A is not a null vector, okay? Because if it's null, it's trivial equation. It doesn't give you anything. So therefore, though this implies lambda is 0, right? That is the only possibility here. And if lambda is 0, of course, what it is saying is y is 0, right? Because if lambda is 0, no matter what the value of x is, y is 0, and then the second equation is anyway automatically satisfied. So, but x is arbitrary, right? So we have one eigenfunction. So we are saying that the solution of this equation, the solution is just x0. This is the solution. So this A acting on that gives you simply gives you 0 times x0, where 0 is eigenvalue. Lambda is 0. This is fine, but you see, this is only, I mean, after all, we had two-dimensional vector space. But this is only, I mean, one component is 0, so this only gives you one-dimensional vector space. You can ask the question, what happens to this if I consider other vectors, 0y? Well, 0y is not an eigenvector of A. I mean, as we said, from this equation, y must be necessarily 0, right? So this is not an eigenvector. However, you can generalize this concept of eigenvector, and that's what is called a generalized eigenvector. So there's a generalization of this concept. So let me just define the generalized eigenvector. This equation I could have rewritten in this form: A minus lambda times identity acting on A is 0. Right? I could have I just brought it to the other side. I mean, identity acting on A is simply A. So this equation is the same. So this is the ordinary eigenvector equation. There is generalized eigenvector equation, generalized eigenvector equation, which is the following. You take A minus lambda times identity to the some power r acting on A equal to 0. I mean, when I write here 0, you understand it is a null vector. This is a null vector there, where so for some positive integer r, but so this is equal to 0, but A minus lambda times identity to the power of r minus 1 acting on A is not 0. Okay. So r is the smallest integer, smallest positive integer, such that A minus lambda e to the power of that r acting on the state A is 0. That's the smallest integer. That's what I mean by this. The fact that I'm saying that this to the power of r minus 1 is not 0 acting on this A, but this to the power of r is 0. So r is the smallest positive integer, right, for this. If you can solve this equation for some lambda and some state A, if you can find a solution, then you say that this state A is a generalized eigenvector of this operator A of rank r. R is called rank. Okay. rank of the generalized eigenvector. So from this point of view, the usual eigenvector is a rank 1 eigenvector, because you see R is simply equal to 1, right? So the usual eigenvectors are rank 1. Generalized eigenvectors are for arbitrary R. R could be 2, 3, whatever. Those are all called generalized eigenvectors. So in this example, I will now show to you that the 0 y, which was not an eigenvector, will turn out to be generalized eigenvector. Okay? I will now show to you this. So let's take this. This is my operator A. Let's consider A minus lambda times identity. Well, what is that? This is simply minus lambda. Identity operator is unit matrix, 2 by 2 unit matrix, right? So this simply minus lambda 1 0 minus lambda, right? This is matrix. Okay. Now let's take the square of this. Let's take so I want to take the square of this, right? So take R equal to 2. So take the square of that. So this will be so A minus lambda E square, which is the square of this matrix. And so what is this? If you multiply this, you get here lambda square, and that one will give you minus 2 lambda. Okay, and here you get 0, and last one you get lambda square, right? I just took the matrix multiplication. So this row with that column will give you 0. This row with that column gives you lambda square. Okay, so just a matrix multiplication. Okay. Now notice that so I want to apply this on say a state of this type 0 y. This was already a usual eigenvector, ordinary eigenvector, but this state was this was missing. This was an extra state in the two-dimensional vector space, right? Which was not an ordinary eigenvector, but we want to check whether this is generalized eigenvector. Okay, and in fact, this is a generalized eigenvector. If you choose lambda equal to 0, this matrix is 0, right? Lambda was eigenvalue, right? So, but if suppose it was a 0 eigenvalue, lambda was equal to 0, then this matrix is 0. So this acting on anything is 0, right? So you see that this, in particular, this acting on that would be 0 if lambda is equal to 0, right? So this vector would be a generalized eigenvector of rank 2 because it's a square, rank 2, right? Because you can see that. You can see that if you had just taken this A minus lambda E and apply it on 0 y, this is not 0. Let's take lambda equal to 0. So lambda is 0, it's 0 eigenvalue. Then A minus lambda E is simply 0, 1, 0, 0. And you want to see whether this acting on this is 0. It's certainly not, because this simply gives you y 0, right? So this is not a 0. This is not a. So this to the power of 1 acting on that is not 0. But this to the power of 2 acting on that is 0, right? So this is a rank 2. It's a generalized eigenvector of rank 2. Okay. Fortunately, this is pretty complicated, as you can see, right? In general, if you give me some operator, it may have some ordinary eigenvectors, some generalized eigenvectors of rank 2, some of rank 3. Who knows? It's a mess, right? In general. But fortunately, it turns out you can prove that for Hermitian operator, all the eigenvectors are ordinary eigenvectors. Fortunately, that's what happens. Huh? So, and since you are always working with Hermitian operators, you will never have to worry about this generalized eigenvector. It's in quantum mechanics, you're always working with the Hermitian operators. So you would not have to worry about this. But in the general classification of all the operators, this play an important role. Let me see. Is there something else I want to see if I have to say something else? Actually, let me try to prove that actually, I mean, because that's a very important point here. So I want to prove that for Hermitian operator, if for Hermitian operators, all eigenvectors are ordinary eigenvectors, are rank 1, generalized eigenvector. I mean, as I said, generalized eigenvector of rank 1 is the same as ordinary eigenvector. So it will be all ordinary eigenvectors. In other words, ordinary. Okay. So let's consider this then. So we are looking at H. H is a Hermitian operator. I will always use the symbol H for the Hermitian. H minus lambda E to the power of R acting on some state A equal to 0. So we are looking at that equation. But so consider a rank R. This is a rank R state. So what we will prove is that R is equal to 1. Rank R. But H minus lambda E to the power of R minus 1 acting on A is not equal to 0. Right? That was the definition of the rank. Okay. So this will be some state. This is a non-zero state. So let's call it B. Some B which is not 0, which is not null. Right? This will be some state in the Hilbert space. Let's take the norm of that. Since this is not a null vector, the norm of this has to be greater than 0. Remember that the scalar product satisfies one condition, that the B with B is always non-negative, and it is 0 only if the B was a null vector. For any non-null vector, it was positive, strictly positive, right? So let's compute the norm. So I mean, what that implies, the fact that it is not null vector, it implies that B with B is positive, strictly greater than 0, right? Okay, but so let's take the dual of B, right? In order to do this, I have to take the dual of B. So what's the dual of B? I mean, since B is defined as that, the dual of B is simply equal to A and the dagger of this H minus lambda E adjoint to the power of R minus 1, right? Correct? That is that's the dual. Well, but then the dual of this, I mean, since, okay, oh, so something I had to prove before. So let's take the dual of that. So that gives you simply A, and the dual of H is the same as, I mean, adjoint of H is the same as H because Hermitian. So you get here H, and lambda is real. I mean, I have to prove also that, but let's assume for the moment that lambda is real. Huh? So assume now that lambda is real. Okay, this is true for Hermitian operators. For non-Hermitian operators, it's not true. Okay, only for Hermitian operators, it's true that eigenvalue is always real. Huh? Okay, so if you so take this, so this becomes H minus lambda E to the power of R minus 1. Okay. So now let's plug that in here. So you find here, this is A, H minus lambda E to the power of R minus 1. That is this B, the dual of the B. And that B is just that. So it's simply H minus lambda E to the power of R minus 1 acting on A. Okay. That's what is this. Okay. I mean, this was simply that B, right? And this part is just the dual of the B. So therefore, so this implies that BB is the same as A H minus lambda E to the power of 2R minus 2, right? The exponents just add up, right? I mean, this to the power of R minus 1, the same operator to the power of R minus 1. So it's to the power of 2R minus 2 acting on A. Okay. But on the other hand, I know that this to the power of R acting on A is 0, right? So for this to be non-zero, I mean, this we know that this is strictly greater than 0, right? So this is strictly greater than 0, right? Therefore, this implies that 2r minus 2 must be less than r, because if this was r or greater than r, that would be 0 because of this condition, right? See, if this to the power of r is 0, this to the power of r plus 1 is also 0, because you can just take multiply by h minus lambda e, this equation. R plus 2, all of the higher powers will be 0, right? So what it is saying is that for this to be non-zero, is 2r minus 2 should be strictly less than r, right? So this implies that r is strictly less than 2, because take this here and minus 2 on the other side, so you get that. So the only possibility is r equal to 1, right? Because r is some positive number, right? And this implies r is 1. Okay. Now, okay, so is that clear?
2r minus 2 is less than her.
Less than r, yeah.
And higher less than 2.
Yes. How did I get that? You subtract from both sides r. I mean 2r minus, so we have 2r minus 2 is strictly less than r, right? So if you subtract from both sides r, this implies that r minus 2 is strictly less than 0. And then you take 2 on the other side, that gives you r is less than 2. Right?
Yes, but I don't understand why you.
Why this equation?
Yes.
Because of this fact, no? I mean, I'm saying that this quantity is greater than 0, strictly greater than 0. So therefore, this must be strictly greater than 0. Now, if this object, if this number, if 2r minus 2 was equal to r or r plus 1, or I mean greater than or equal to r, okay, then this operator acting on a would be 0. So I mean, take for example, suppose this 2r minus 2 was equal to r, okay, then this acting on that is 0 because of this equation, right? I mean, this equation implies that, for example, h minus lambda e to the power of r plus any number, where n is some non-negative integer, this acting on a is also 0, right? Because I can take this equation and multiply by h minus lambda e to the power of n, right? Then you get that. So whenever 2r minus 2 is greater than or equal to r, this operator acting on a is 0 from that equation. So the only way this can be non-zero is if this 2r minus 2 was strictly less than r. You see, that's the reason. Yeah. So that's a very important result. I mean, saying that for a Hermitian operator, if there is a generalized eigenvector, it is necessarily of rank 1, right? Which means it's ordinary eigenvector. That's an important point. And finally, the only thing in proving this, I assume that lambda was real, right? So now I have to prove that lambda is real. So that let's see, that we can prove in the following way. Okay, so let's see. H. In fact, let me first look at the simplest case, usual eigenvalue. Usual eigenvector, ordinary eigenvector, which means HA equal to lambda A. Let's consider this. So this is our ordinary eigenvector. Okay. And then I'd like to prove that lambda is real. I mean, a priori, there's no reason why lambda should be real, right? If this was an arbitrary operator, lambda may not be real, right? But for Hermitian operator, this will be true. So how we can prove that? So let's take the scalar product of this with the dual of A. So you have that, right? So on the right hand side, you get lambda AA. Right? But this by definition of that joint is simply A, H dagger, A complex conjugate, right? That was the definition of that joint. But now we are saying H is Hermitian, so H dagger is H. Okay, so this gives you, this is the same as A, H, A complex conjugate. But HA is lambda A. So what we are seeing here, this is equal to complex conjugate of lambda AA complex conjugate, right? Because the H of H acting on A is simply lambda times A. Lambda is a number, you can take it out. Then this just simply gives you lambda AA, square product of A with A, and take compute this and take the complex conjugate of the whole thing. Okay, but that's the same as lambda bar, lambda complex conjugate of lambda, and then complex conjugate of A with A, but that is a real. Remember that was one of the conditions. In fact, it is non-negative, strictly positive, right? And okay, I'll always assume that A is a non-null vector, because as I said, if it's null vector, it's a trivial statement, right? So if A is not null, this is greater than 0, real and greater than 0. So complex conjugate of that will be the same as AA. Right? So we have proven, I mean, on the one side, this is equal to that. On the other side, by using the fact that this is Hermitian, it's also equal to that. Right? So this can only be true if lambda is equal to lambda bar. Okay, that's real. Yeah. I think you should be able to prove also in general. This was for ordinary eigenvector. Let's see if we can prove in general. So we are looking at this to the power of r acting on some state A equal to 0, right? So let's see if we can prove this. If I now take the scalar product of this here, so that's equal to 0. Or maybe not. Maybe you should. I think you have to do it recursively, but I'm not sure. So now if I take, so I can take the complex conjugate of that. So this is the same as A, then H minus lambda E bar, I mean dagger, to the power of r acting on A, complex conjugate. So this will be H no, I think no, this is not going right. No, I mean, I'll have to think about it, how you can generalize. This is for the ordinary eigenvector, okay? But you can prove also in general. I mean, if I mean, I don't need to prove it because I've already shown that this, if H is Hermitian, then on the one side, ordinary eigenvectors have real eigenvalue, right? And second point I tried to show, although I have made an assumption there, but second thing I showed was that for Hermitian operator, r is always equal to 1. So I don't need to do that. But you can also actually, in general, without doing this, you can still prove this, okay? That the lambda has to be real, okay? If the H is Hermitian, then for any generalized eigenvector, lambda must be real. But okay, let me try to prove that next time. I mean, no, it should be not very difficult to prove this, but how does it go? I have to think this about this because I see that in the notes is only proven for the real, for the rank 1 case. Yeah, you can, actually it's very simple in fact. Yeah, so the way to prove is the following. Suppose I have a generalized eigenvector. So h minus lambda e to the power of r is acting on a is 0, but h minus lambda e to the r minus 1 acting on a is not 0. Okay? That was the definition of generalized eigenvector of rank r. But then, if this is not equal to 0, it will be some vector, non-null vector b, which is not 0, right? So I can rewrite this equation in the following way. I can rewrite this equation as h minus lambda e times h minus lambda e to the power of r minus 1 acting on a equal to 0, right? I have just separated out, written this r as 1 plus r minus 1. But this guy is b, okay? So this implies that h minus lambda e acting on b is 0, right? Because this whole thing is b. Okay. Then for the vector b, for the state b, this is just an ordinary eigenvector, right? I mean, so just open this up. So this implies that h acting on b is lambda acting on b, lambda times b, right? Because lambda e b is simply lambda b, and take it on the other side. So you see that even for a generalized eigenvector of rank r, if you call this state as some state b, which is a non-zero, non-null state, then b is an ordinary eigenvector. Okay. Okay. And then this proof works. Huh? Then this proof is already there. So instead of a, just write it as b. Right. Write this as b. Then this proof works. Right? I mean, this proof that I gave. Right? And then you take the use the Hermitian property. Then you find it's lambda bar. Okay. So this is the idea. In fact, yeah, maybe I should have mentioned this. The general structure. You see. So if I take a rank r eigenvector, so what we'll have? I mean, so we'll have h minus lambda e, now for arbitrary operator a, okay? Now not necessarily Hermitian, any operator a to the power of r acting on a is 0, some state, but a minus lambda e to the power of r minus 1 acting on a is not 0. Okay? Let's call this some vector, let's say b, let's call it b1. Okay. But then also you see a minus lambda e to the power of r minus 2 is also not 0, right? This cannot be 0, because if this was 0, then this would have been 0, right? Because you just apply 1 a minus lambda e to this, you get that, right? 1 power of a minus lambda e, if you apply on this, you will get that. If this was a null vector, then this would be also null vector. So this is also not null. So call this as b2. Again, these are all not null. And you keep going down. Okay? So all the way up to a minus lambda e acting on a, which I don't know what will be the number. Maybe let me label it like this. So this is r minus 1, this is r minus 2, all the way up to this is simply 1, b1. Okay? And finally, just the state a itself, which means this to the power of 0, which means state a. So all of these states are there. You see, one generalized eigenvector a actually defines to you several set of vectors here. Okay? This vector is an ordinary eigenvector of rank 1 for the reason I mentioned. Because if you now apply just one more power of a minus lambda e, then that annihilates it, which means a minus lambda e acting on this is 0, right? So this is an ordinary eigenvector of rank 1. You can show that this vector is rank 2 eigenvector, rank 2 eigenvector. The next one will be rank 3, and so on and so forth. Okay? So there's a whole sequence of vectors. You can define, once you have a generalized eigenvector, you can define this whole sequence of vectors, which are all not null, and they have ranks ranging from r up to, this has rank r, that will have rank r minus 1. Okay? And finally, the last one, this one will have rank 1. So this whole sequence of vectors you can define, which have different ranks, ranging from R up to 1. Okay. So this is a general statement. Yeah. And so in particular, this proof we gave for the for the ordinary eigenvector, that will go through also for generalized eigenvector, because in this sequence there is always one vector which has rank 1, right? And that must satisfy that lambda is real for Hermitian operators. For Hermitian operators, so this is it.